Okay, so when dealing with collision problems or conservation of momentum problems, there's going to be two basic cases, bouncing and or sticking, right? And so the first example we're going to explore is bouncing. And the most basic example is billiard balls, where we have one ball moving with some initial velocity, and we have a second billiard ball, in this particular case, not moving. We can move these to a more advanced level with having this move in opposite directions and all kinds of other stuff. But for now, the simplified case for an example. So after they collide, somewhere here in the middle, we know that ball 1 and ball 2 are smacking together and bouncing off. And the after case, we're presented with the information that V2 moves off with some new speed and V1 changes. We're not quite sure if it comes to a stop, and we're not quite sure if it rebounds or moves forward, and so I'm going to go ahead and leave off an arrow and be sure to not presume anything until I'm finished. The basic format that's I find to be most effective is to really think about the equal sign as your before and after. And so we're just going to start with the momentum of the system equal to the momentum of the system after the collision. And so the first thing is to parse out what the pieces of the system are. So obviously in this particular case, I have momentum 1 plus momentum 2, identifying momentums of any individual piece within that closed system. Therefore, I should expect that on the after side, I have momentum 1 prime as a vector plus momentum 2 prime as a vector. And so we see conservation of the total system equal to the total system after. Once you've got that established, right, then we can go through and identify some of the characteristics of the overall problem. We want to be careful to not forget a frame of reference, since all of these things are directional variables, at least as far as the momentum and the speed. So if I define going to the right as positive, then I would say that this ball has a V1 that is some positive number here. I would say that V2 in this particular case is 0, and then V1 prime is some unknown, and V2 prime is some positive number. And obviously that would change depending on the situation. That being said, I also know that momentum is dependent on mass, so we would define this as M1, we would define this as M2, M1, and M2. I'm careful to not put the primes on the right-hand side, and this is simply a case of the fact that the mass of interacting objects generally does not change, right? It's very rare that we would see that M1 is not consistent with what it was before the collision, explosion, whatever it may be. That becomes very useful because that means that in our equations we may have like terms that we can factor out despite the fact that they exist before and after. Once you've separated the individual pieces of the system's momentums, then it's just a matter of adding in the knowledge that we know that mass times velocity is momentum. And so we have these as vectors plus M2 V2 as a vector equal to, sorry about the dotted line there, M1 V1 prime as a vector plus M2 V2 prime as a vector. So generally, this would be the generic form for a bouncing collision. But I like to remind you that really it's the momentum of the system equal to the momentum of the system afterwards, because this is a generic case of just two objects bouncing off of each other. And obviously, we could have a complex system that has more parts. We could also have a complex system where we have multiple dimensions, and then this equation does not hold true. So this is a very isolated example in this particular case.